All right, welcome to Chemical Analysis, Empirical Formula. We're going to go over the basics of empirical formula, and then we'll get into some more complicated problems. So as a quick review, go ahead and pause the video right here. Try to calculate the volume in liters of 12 grams of hydrogen gas at STP, and also try to figure out the percentage of oxygen in silver 1 nitrate. So these should be fairly easy for you to do. All right, so you should be able to set up this problem by writing our given. So we have 12 grams of H2, and the molar mass of H2 is 2 grams, right? So 2 hydrogens times 1 gram per mole on the periodic table is equal to 1 mole of hydrogen of H2. And then from there, we can use the beautiful ratio of 1 mole is equal to 22.4 liters because it's at STP. So 1 mole of H2 will go on the bottom and 22.4 liters can go on the top. Then we multiply the top, divide by the bottom, we end up with 134.4 liters of hydrogen or H2 gas. In order to find the percent of oxygen in silver 1 nitrate, we have to first and foremost write what it is, right? So silver 1 is Ag plus 1 because 1, the Roman numeral 1, tells us the charge. Nitrate, we hopefully have it memorized, is NO3 minus 1. So when we cross our charges to balance them to make them neutral, we just need one of each of these. So we have AgNO3. In order to find the percent oxygen in this equation, in this compound, we first need to find the total molar mass. And so I know for Ag, I have 1 Ag, I have 1 nitrogen, and I have 3 oxygens. And I'm going to multiply it by the molar mass that I can find off the periodic table. And so oxygen I know is 16, nitrogen I know is 14, and silver, we're going to have to look it up if we don't have it memorized, is 107.9. And so then from there, we multiply everything out and we add it together to find our total molar mass. So go ahead and pause the video and do that. All right, so you should have gotten about 169.9 grams per mole. And so we multiply each of them and then add them together. And then oxygen on the bottom, if we just take oxygen by itself, so 3 times 16, that's 48. And so in order to find the percent of anything, it's always part divided by our total. And so our part of oxygen is 48, our total is 169.9, and to put it into a percent, we multiply by 100. And so we have 48 divided by 169.9 times 100 gives us about 28.25% for oxygen in our total compound right there. All right, go ahead and try this one. You're going to try to find the mass percent of carbon, of hydrogen, and of oxygen. So you want to find the percentage of carbon, so it's going to be the part that carbon weighs divided by the total molar mass. Same thing for hydrogen, and the same thing for oxygen. I'm not going to do this one because I hope you guys find this pretty easy. Alrighty, so the next part is empirical versus molecular formula. So empirical formula is our simplest integral ratio of atoms in a compound. Right? So the key word here is simple integral ratio. In other words, it's the percent composition of a compound. Whereas the molecular formula is the actual number of atoms in the compound, or the actual molecular weight, the molar mass of the compound. So if we look down here, EF stands for empirical formula, MF stands for molecular formula. Let's look at a couple of these examples, right? So we have water as the empirical formula and water, H2O, as the molecular formula. They're the same in this case. Whereas the next one's down, this one right here is formaldehyde, this one right here is a compound that I can't remember, and this one is glucose, right? So they're all different compounds, but if you notice, they all have the exact same empirical formula. So empirical formula, what exactly is it? It is just, again, the simplest integral ratio of atoms. And so if we look at the left side for all 3 of these right here, the simplest integral ratio of these, there's 1 carbon to every 2 hydrogens to every 1 oxygen, right? So it's a 1 to 2 to 1 ratio. If we look at these 3 on the right side, the molecular formula, we have a 2 carbons to 4 hydrogens to 2 oxygen, so it's a 2 to 4 to 2 ratio, but that can be simplified down to a 1 to 2 to 1 ratio. So the empirical formula is basically like a fraction, think of it that way, or a ratio, relative atoms to each other, right? This one is just a 1 to 2 to 1 ratio, formaldehyde, and then we have a 6 to 12 to 6 ratio, which again can be simplified down into a 1 to 2 to 1 ratio. So empirical formula is just the simplified version, whereas the molecular formula is actually how many do you actually have to make this compound. And so how is the molecular formula different from the empirical formula, right? It is a multiple. The empirical formula, the molecular formula is a multiple of the empirical formula. And can the molecular formula be the same as the empirical formula? Yes, it can be the same, as we saw in this case right here and in this case right here. Right, so if we look at benzene, another example right here, benzene is C6H6 and acetylene is C2H2. If we reduce down those empirical formulas, it's just a 1 to 1 ratio for both of them. And so even though these are completely different compounds, they each have their own ratio, right? This can be reduced down to 1 to 1 because 6 to 6, right, can go into each other, and same with 2 to 2. And so the empirical formula in this case is just 1 carbon to 1 hydrogen. So we have to be careful about the empirical formula when we have to find a molecular formula. All right, so the empirical formula poem, percent to mass, mass to moles, divide by the smallest, and multiply till whole. We're going to use these steps right here for even the most complicated chemical analysis problems. It's always those 4 steps right there. As a couple of side notes, on step number 1, percent to mass, always assume that percentage is out of 100%, and so therefore we can assume that it's out of 100 grams. The second and third steps, when you convert mass to moles using your atomic mass, relative masses off the periodic table, and also when you're dividing by the smallest number, avoid rounding, be lenient with your sig figs. If you round too soon, or if you cut off the numbers when you are going from mass to moles and dividing by the smallest, it tends to give you the wrong answer sometimes. And then the last one, multiply to a whole. If the ratio includes a recognizable fraction, then you need to multiply it by the appropriate number. And what I mean by that is, say you end up with, at the very end, 2.5. This is a recognizable fraction, right? 0.5 is the same thing as 1/2. And so you need to multiply it by an appropriate number to get it into a whole number. And so in order to get 1/2 into a whole number, we multiply by its reciprocal, which in this case is 2, right? And so then we would get it into a whole number, right? So if we multiply 2.5 by 2, we would get it into a whole number of 5. And so we'll go over a couple examples where that will occur. Right, so the first example here says, determine the empirical formula of a compound that is 52.8% tin, 12.4% iron, 16% carbon, and 18.8% nitrogen. And so our very first step is percent to mass. So we're going to take all of these percentages and convert it to mass. And again, we're assuming that it's out of 100%, so we can just take it into out of 100 grams. So 52.8% turns into 52.8 grams of tin. We have 12.4 grams of iron. We have 16.0 grams of carbon. And last but not least, we have 18.8 grams of nitrogen. That's our first step, easy peasy. Our second step is to go from mass to moles. In order to go from mass to moles, we use the relative atomic mass, aka the molar mass off the periodic table. So we need to look up the molar mass of tin on the periodic table. And on my version of the periodic table that I have in front of me, tin is 118.71 grams for every 1 mole. Iron is 55.845 grams for every 1 mole. Carbon, I'm just going to go ahead and round that one to 12. And nitrogen, I'm going to round that one to 14. All right, for this step right here, be lenient, write as many of the decimals as you can, just because if you round it too soon, it might cause rounding error. So go ahead and pause, see if you can calculate this. I'll go ahead and write the answers down in a second. All right, so these are the answers that I got. So 0.444, 0.222, 1.333, 1.342. From this part, we're on the third step of our poem. It is to divide by the smallest number. And so we're going to look at all of the numbers that we just calculated, right? And so we're going to look at all the numbers we just calculated. And these are the 4 numbers we just calculated, right? And out of those 4 numbers, which one is the smallest? So 0.222, that one's the smallest. So we're going to go ahead and divide each of those numbers by 0.222. So we're going to take the first one and divide it by the 0.222 number. We're going to take the second one and divide it by itself. We're going to take the third one, divide it by the 0.222, and same thing with the fourth one. All right, from here, go ahead and pause the video. I'll pause the video and then I'll write the answers down. Alrighty, so when I divided the first one, I got a number of 2, and 1, and then 6, and then 6. So those are our simple integral ratios, our simplest whole number ratio for this particular compound. And so when we write our answer, I'll write it up at the top in purple. We're going to go ahead and write those numbers as the amount of atoms that we have in our compound. And so our first one was iron. And so, tin. So we have Sn, and there's 2 of them. So there's going to be a little 2 right there. And then the next element was iron, and there was 1 of them. The next element was carbon, and we had 6 of them, and nitrogen also had 6 of them. So that is our empirical formula for this compound. All right, the next one right here, it says a sample of a compound contains 5.723 grams of silver and 0.852 grams of sulfur and 1.695 grams of oxygen. Determine its empirical formula. And so for this one right here, we're going to do the same idea, same thing, where we start with what they gave us, and in this case it's grams. And so we are going to skip the whole first step of the poem, percent to mass, and we can just go mass to moles. And so we start by writing what we're given, so 5.723 grams of silver. Then we have 0.852 grams of sulfur, and we have 1.695 grams of oxygen. All right, from here we want to go from mass to moles, and so again, use the molar mass off the periodic table. Oxygen at the bottom is 16 grams of oxygen for every 1 mole of oxygen. Sulfur on the periodic table, I'm going to go ahead and round that to 32. And silver on the periodic table is 107.87, let's say, for every 1 mole of silver. All right, from here, we need to divide it. So go ahead and pause and see if you can divide. All right, so I kind of rounded a little bit, but again, be lenient with your significant figures here. Don't round it too much. The sig figs don't matter in the middle of the calculation. They only matter at the end for your answer. So out of these 3 numbers in orange, which one is the smallest? And so we have 0.05, 0.02, and 0.1. So I know by looking at those, 0.02 is the smallest out of them. And so I'm going to take 0.02 and I'm going to divide each of them by 0.02. All right, once I have each of those divided, that will give me my simplest integral ratio. All right, so this one right here at the bottom, I rounded it up to 4, right? So on your calculator, when I calculated it, it was 3.9. So round it up, right? So round it to the nearest whole number if possible. If it's a recognizable fraction, though, then you have to multiply to the whole. So in this case, we have 2 silvers, so Ag2, and we have 1 sulfur, and we have 4 oxygens, and that's silver sulfate right there. So that one makes sense. All right, I would like you guys to try this one on your own. As a tip, it says the rest is oxygen. And remember that it's out of 100%. And so out of 100% means we can take 100% and we can subtract the carbon, the hydrogen, and the nitrogen in order to find our percent that's missing for oxygen. And then we do the same thing, percent to mass, mass to moles, divide by the smallest, multiply till whole. All right, so let's go through this one. I'm gonna go through it pretty quickly. I'll pause it, and so the video will kind of fast forward just for the sake of time. So percent to mass, convert it to grams. And then mass to moles, convert your grams to moles of each of those elements, and then divide by the smallest. All right, so hopefully you got the numbers 7, 9, 1, and 2.5. And so when I say multiply to whole, if you recognize a fraction, in this case, right, we recognize 0.5 as a 1/2 fraction. So this is not 2, it's not 3, it's right in the middle, so we can't round it up, we can't round it down. It's 2.5. And so 2.5 is, again, 0.5 is 1/2, so we multiply it by its reciprocal. So multiply to whole just means multiply it by the appropriate number to get rid of that fraction. And so in this case, we're going to multiply the bottom one by 2. So I'll do that in green, and then multiply this by 2. And what we do to one of those numbers, because it's a ratio, we have to adjust all of the numbers. And so we have to multiply all of them by 2. So now we have 14, we have 18, we have 2, and we have 5. So our simple integral ratio in this case, we have carbon is 14 of them. We have hydrogen at 18 of them. Nitrogen has 2 of them, and oxygen is 5 of them. And so that is our empirical formula, which in this case, NutraSweet happens to be our molecular formula as well. All right, so molecular formulas are not are just the actual formula. They're not just the simplest integral ratio. All right, so they are the actual formula. They're not the simplest integral ratio. They're not just the simplest integral ratio. The molar mass of the empirical formula is always a multiple of the molecular formula's actual weight. And the last one, it says use the molar mass of the empirical formula and the molar mass of the molecular formula to determine by what factor you need to multiply the empirical formula's integral ratio to find the molecular formula's actual compound. So let's do an example of that one. So we want to find the empirical and the molecular formula in this case, and we're given the percentages, and we're also given the molar mass. Right, so whenever you're given the molar mass, that is the molar mass of the molecular formula. So go ahead and pause the video and try to calculate the empirical formula based on those percentages right there. All right, so hopefully you got Cl as 1, carbon as 1, and hydrogen as 2. So our empirical formula I wrote up at the top left in green, 1 chlorine, 1 carbon, and 2 hydrogens. In order to find the ratio or the multiple to multiply to the empirical formula to find the molecular formula, we have to find the molar mass of the empirical formula. And so our molar mass of this empirical formula right here, we have 1 chlorine plus 1 of the carbons plus 2 hydrogens. And so we end up with a molar mass of 35.5 plus 12 plus 2. Okay, so that's the mass of chlorine plus the mass of the carbon plus the mass of the 2 hydrogens, which is 49.5 grams per mole. All right, so the empirical formula weighs about half of the molar mass. The actual molecular formula's molar mass. And so we're going to divide those 2 molar masses to find the multiple to multiply the empirical formula to, or by. And so I'll do that in blue off to the side. We take 98.96 divided by 49.5. So we're basically taking the molecular formula and dividing it by our empirical formula. And when we go ahead and do that, we end up with approximately 2. So our multiple that we're going to multiply to the empirical formula is 2. So what does that look like? So we have 1 chlorine, we have 1 carbon, we have 2 hydrogens. We're going to multiply it by 2 because, again, that is our multiple in order to get from the simplest integral ratio to the actual formula. So our actual formula is 2 chlorines, 2 carbons, and 4 hydrogens.